Alrighty, so today we're going to be talking about nuclear decay series and balancing nuclear reactions. And this is really just going to be an introduction for us, a brief introduction on nuclear chemistry. We're going to focus more on that after the break. After the semester ends. But I do want to get, since we're talking about balancing reactions right now, I do want to talk a little bit about balancing nuclear reactions, because they are a type of reaction. So the first thing to think about is the fact that there are multiple different types of decay in radiation or radioactive chemistry. And there are three different types that we're going to be looking at today: alpha, beta, and gamma radiation. And there's a fourth type, neutron, but we're not going to be talking about that right now. Specifically, we're going to be looking at alpha, beta, and gamma. And so alpha decay occurs when an unstable nucleus emits a helium nucleus, or an alpha particle, and decays into a new stable nucleus. Now, an alpha particle is represented by the Greek letter alpha, and it is a helium nucleus, meaning that it contains 2 protons and 2 neutrons. And so you have to make that balance in the reaction that you're representing. So if we look at an example, here we have, here we have platinum 175. So it has 78 protons, and let me do the math really quick. Minus, not multiplied. 97 neutrons. And so when it undergoes alpha decay, it's going to release 2 protons and 2 neutrons, so a total of 4 atomic particles. And so it's going to release 2 protons to go from 78 to 76, and then 4 protons plus neutrons, so 4 total. So it goes from 175 to 171. Now, jumping down from 2 protons, from 78 to 76, takes you from platinum down to osmium. Okay, and the way that you do that is just look at the periodic table, and 78 was platinum, and 76 is osmium. And then you just have to get the top and the bottom numbers to balance on the left and the right side of the equation. So remember, we're emitting this radiation, so it becomes a product, and then our reactant, or our product changes, our element changes. Nuclear decay is the only type of chemical reaction that actually changes the element that you're looking at. This is the only type of thing where the element changes. And it doesn't always change the element. But if you're changing the number of protons, you are changing the element that you're talking about. We talked about that way back in Unit 2 when we started talking about the periodic table, and that as you increase the number of protons, you change elements. So kind of keep that in mind. Now, beta decay is represented by the Greek letter beta. Beta decay occurs when an unstable nucleus converts a neutron into a proton and an electron. So it has to go from a neutron into a proton and electron in order to stabilize its charge. Because if it just converted a proton into a neutron, then it would become an ion, because it's taking a 0 charge to a positive charge. But if it converts a 0 charge to a positive and a negative, a proton and an electron, then that balances out and you don't have any charge differential. The proton remains in the new stable nucleus, but the electron is ejected. So what that looks like is something like lithium. So lithium has 3 protons and 5 neutrons, and what happens is that one of those neutrons becomes a proton, and so the 3 becomes 4, and then it emits 1 electron. Now, your overall total number of nucleons, or protons and neutrons, remains the same, because you lost a neutron and you gained a proton, so you lost from 5 neutrons you went down to 4, but from 3 protons you went up to 4. So 4 plus 4 still equals 8, just like 5 and 3 did. But in order to balance this reaction, the electron down here has a -1. That's just kind of how we represent electrons in nuclear chemistry. But that also means that 4 minus 1 is 3, and it stays balanced. Okay, we're learning all sorts of new stuff today. And then you can have gamma decay, represented by the Greek letter gamma, where an unstable nucleus emits energy as a gamma ray to stabilize the nucleus. So this is the only one where the number of protons and neutrons isn't being affected at all. An unstable nucleus is just emitting energy. So it's not emitting any sort of particle, but rather a gamma ray as energy. And so here Cobalt-60 is emitting a gamma ray to remain Cobalt-60, just stable Cobalt-60. And so here, there is no balancing that needs to be going on. It's just that it emits a gamma ray, so it's emitting energy. Now, this is very useful for us later in nuclear chemistry, in the field of nuclear chemistry. It's very important to know what's going on with those gamma particles, or those gamma rays, and to know the energies that they're emitted at and the half and all of that. And so we'll get into that when we start talking about nuclear. But I wanted you guys to just know about balancing those types of reactions. And so we have alpha, beta, and gamma. Alpha and beta, the actual element is changing, and in gamma, it's not. But again, throughout, we have to keep the top and the bottom balanced. So our total number of nucleons and our number of protons balanced. Now, I do want to mention one more thing before you click off, and that's the idea of a nuclear decay series. And what this means is that sometimes one decay is not enough in order for an element to be stable. Those really, really heavy elements, as we call them, meaning that they've got lots of protons and neutrons, those radioactive elements, those heavy elements, sometimes it's not just enough to emit 2 protons and 2 neutrons. The biggest radioactive decay you can have, an alpha decay. Sometimes that's not enough to get to stability, and so it has to undergo multiple different decay series in order to get to stability. So an unstable nucleus will continue to decay or emit radiation until it reaches a stable nucleus. And a decay series will show the different transformations of an unstable nucleus that it's going to undergo in order to reach stability. So for example, uranium-238, in order to decay, it actually goes through, sorry, I'm counting really fast, like 14, I think I counted that, right? 14 different decay reactions in order to get to stability. So first it emits an alpha to go from uranium-238 to thorium-234. Then it betas into praseodymium, I think, PA, I can't remember. Yeah, protactinium, sorry. Protactinium-234, which betas into uranium-234, which then alphas into thorium-230, which alphas into radium-226, which alphas into radon-222, which alphas into polonium-218, which alphas into lead-214, which betas into bismuth-214, betas into polonium-214, alphas into lead-210, which betas into bismuth-210, which betas into polonium-210, finally alpha decaying into lead-206. Now you'll notice that lead-206 is actually, lead is typically, different isotopes of lead is the typical endpoint for stability, and that's just partially to do with the stability of lead and its ratios of protons and neutrons. But a decay series, again, just shows you the different steps that these elements take to get to stability, and I just want you guys to be able to balance this out. And I would never ask you to know exactly what's going to occur. I would either give you like these reactions but not give you the type of decay that's going on and ask you to identify the type of decay, or I'd tell you that uranium would alpha, then beta, then beta, then alpha, then alpha, then alpha, and ask you to go through those decay series. I don't expect you to know what type of decay it's undergoing, I just expect you to be able to balance that type of decay. So we'll talk more about this next time, and have a good night.